Well, in this lecture, we're going to be looking at going deeper into this concept of constitutional isomers. Now, I'm going to be on camera a little bit because I have some model kits that we're going to use, and just to kind of show, like, if we have a formula, how many different ways can we connect all these atoms together? And again, just to review this concept of constitutional isomers, these are compounds with the same molecular formula, but different connectivity. So if you're given a molecular formula, you should be able to draw out a number of constitutional isomers based off of the atoms that are there in that molecular formula, and as well as using those concepts we've already talked about before with common bonding patterns between atoms with like carbon or nitrogen or oxygen. And so that's what we're going to work on today is if you're given a molecular formula, can you draw a number of constitutional isomers? So let's jump right in and we're going to look at this first example. Draw all the constitutional isomers of C3H8O. Now we're just going to kind of operate just in the beginning. I'm going to kind of go like from a little bit of a slower process and just kind of go like, how do I even know what atoms are connected to what? So we'll go all the way back to what we were doing with like Lewis structures. And let's just kind of put all the carbons in a row and then oxygen on the end. And I'm going to fill in the spots and say, well, let's just assume, see if it works. If I put hydrogens on all the carbons, you'll notice I'm there with like, there's 7 right now. So I'm going to put the last one on the oxygen. And so let's draw the skeleton formula for that. I've drawn the kind of expanded formula, but let's draw the skeleton formula. So I'm going to have, there's my carbons. So 3 carbons. And on this carbon on the end, I'm going to put the oxygen or put that OH group. Essentially, that's what we have here with this model. So we have our 3 carbons in a row, and then this will be our oxygen, and then the hydrogen on the oxygen. I don't have enough these white spheres to kind of, fill in all the hydrogens, but let's just assume all of these carbons have hydrogens on them. Okay. So this is one constitutional isomer. Now, how do I get to another one? Well, what I'm going to do is I'm going to mess with the connectivity. Let's say, what if I were to take the OH off of the end here, and instead of having it in the carbon here, I'm going to put it here in the middle. So now that oxygen is no longer on this carbon on the end. It's now attached to the one in the middle. You can kind of turn it there and you can see it kind of sticking out right at you there. And so how do I draw that as a constitutional isomer? Well, I still have 3 carbons in a row. So I'm going to draw that. And I'm going to put the OH on the second carbon. Now, if you want to like verify that, yeah, these are actually constitutional isomers, let's just number these carbons. So 1, 2, and 3. And I'll number these here, 1, 2, and 3. So there you can see that the OH here is attached to that second carbon, the carbon in the middle, and not on the carbon on the end. Now, that seemed to work out really well where I started off on this end, I took it off and put it on this one. Let's take this off again, and I'm going to put it on the other end. Okay. Now, I want you to look very closely at this. Okay. Is this any different than one that we've already drawn? You say, well, it's on a different carbon than before. All right, but let me show you something kind of peculiar. And this is why model kits really help with this. All right, so this isn't magic. I'm not going to rearrange anything else. All I'm going to do is turn this compound around and look at what we get. We get right back to the very first one that we drew. So doing this, oops, is the same as our first one. That's not an isomer, that's an identical compound. Just like you spinning around in a circle doesn't change who you are, spinning a molecule around, whether oriented like this or like this or like this, it doesn't change its identity. That OH is still on a carbon on the end. Okay. And so these two structures are not isomers, they are identical to each other. So we have one isomer here. This is a constitutional isomer. Can you think of another way to rearrange this to get, there is one more possibility. I want you to pause the video. I want you to think about it. If you have a model kit, put it together. And I want you to think about another way that you can arrange the structure of this. Okay. So instead of having the oxygen on the end with the hydrogen on it, what I'm going to do is I'm going to take that hydrogen off here, and I'll just kind of put it on a random carbon. And instead of having the oxygen be off on the end, I'm going to make it part of the chain. So I'm going to physically, notice I'm physically taking this apart. I'm physically disconnecting everything. And now I'm putting it as part of the chain. So if I'm going to draw the skeleton formula for this, I got two carbons, and then this carbon's bonded to an oxygen, and then that one's bonded to a carbon on the end. So I'll number these atoms here. 1, 2, 3, 4. So here's atom number 1, that carbon. Here's atom number 2, the oxygen, and then 3, and then 4. And you'll notice that's a much different connectivity than either isomers 1 or 2. Now, again, just like we saw with isomer number 1, putting the oxygen on this side does not make it a new isomer, because all that is I'm just rotating it around like this. So these two compounds are exactly the same, not a different isomer. Okay, so what I encourage you to do, work with this, put the video on pause, go to some of the problem set problems, and go to the ones that recommend or that ask you to do to draw constitutional isomers for a molecular formula. If you're having problems trying to do that, I highly recommend come to see me during office hours. But let's continue on with another example. So good idea, pause the video, try some problems. Look up in one of your textbooks, try some problems, and then see if you can discover all the constitutional isomers. So let's go now to the next one. So draw all the constitutional isomers of C5H12. Now, what I'm not going to do is I'm not going to go through this thing I've done before where I'm going to like, okay, I'm going to put all my carbons here. I'm not going to do that. Okay. Because now hopefully you're kind of catching on to a trend. In organic chemistry, carbons are going to be attached to each other. So the easiest starting point when you're given a molecular formula and you're supposed to draw these isomers is the easiest one to do. Just draw all 5 in a row. Just do like 1, 2, 3, 4, 5. Just put them all in a row like that. And there's your first isomer, your first isomer. And again, I encourage you like go through, you can see where all 12 of those hydrogens are, practice your skeleton formulas, but I'm going to go do the same thing I did before. Here's a model kit of this. So I got, doesn't want to stay together, 5 carbons in a row. And there's no other way to draw this with 5 in a row. So what I'm going to do is I'm going to take one off. I'm going to take one off the end here. And I'm going to put it not on an end. I'll put it like maybe here on this second carbon. So now it's on the second carbon here, hanging off of this side. So I want to emphasize, I got 4 carbons in a row. 1, 2, 3, 4. So let's draw that. 4 carbons in a row. Here's my skeleton formula for 4 in a row. And on this one right here, or I should say this one right here, I have another carbon hanging off here. Okay, so it's the same formula. I didn't take away any atoms. I just took 1 carbon off of here and I put it somewhere else. Now, just like we did on the previous problem, If I take this carbon off here and I put it on this carbon here, that's just the same as if I were spinning the molecule around. So doing this is not a new isomer. It's exactly the same as that one. So I'm kind of done with 4 carbons in a row. So is there another possibility? Well, what if instead of having 4 carbons in a row, I'm going to take 2 off and I'm going to start here with 3 carbons in a row. And I'm going to take those other 2 and I'm going to put them right here in the middle, attached to the same carbon in the middle. So when we draw the skeleton formula for that, here's my 3 carbons in a row, 1, 2, and 3. I'm going to rotate this a little bit. On this middle carbon, I have 2 additional carbons attached. So I'm going to draw 1 here and 1 here, like that. If you want to draw it like this, that's okay as well. Okay. Now there is no other constitutional isomer. There's no other way I can do this. You say, well, what if you do 2 carbons in a row? And I encourage you to try this. If you have your model kit, just, start with 2 carbons in a row here, and then put your other 3 on here. And anything in any arrangement that you want, you will find that you will get either number 1, 2, or 3. Okay. So there is no other possible isomers that you can draw for this molecular formula of C5H12. All right, now the last thing I want to highlight in this video is common formal charges in OCHEM. Now, I told you at the very beginning, the very first lecture, that knowing how to calculate formal charge is something that you just have to do. In OCHEM, there are some very common trends where you can be able to look at any of the atoms like carbon, nitrogen, or oxygen and be able to tell what its formal charge is just by looking at what it's attached to and how many lone pairs it has. You don't have to go through the formula of how do I calculate formal charge. But this is going to be super important because it's basically a shortcut so that you don't have to do a calculation every time you want to know the formal charge of an atom. So I'm going to go through the 3 most common atoms, and that's carbon, oxygen, and nitrogen. So if you see a carbon atom that's got 8 bonding electrons around it, which means no lone pairs, its formal charge is always 0. So just like an example of that, here's a carbon that's got 8 bonding electrons around it. Its formal charge is always 0. Or something like this. These carbons all have 8 bonding electrons around them. So its formal charge is 0. Don't have to do a calculation. You know it fits that trend. So it's got to have a formal charge of 0. If you see a carbon with 6 bonding electrons with no lone pairs, okay, again, circle, highlight, star that, no lone pairs, it's going to have a formal charge of +1. You say, wait a second, that carbon's not happy. Yeah, it doesn't have 8 electrons around it. It's not happy. It's not super stable. We'll talk more about this in a little bit, but it is, we're going to see this pop up quite often, where a carbon will have 6 bonding electrons around it and have a positive charge. Okay, we'll come back to this in another chapter, but we call that a carbocation. And then a carbon with 6 bonding electrons and 1 lone pair will have a formal charge of -1. So an example of that would be something like this. 6 valence electrons are on our bonding electrons, sorry, and we'll have a lone pair and a -1 charge. We call that a carbanion. All right, so those are, three types of carbons. Commit that to memory so that you'll be able to look at any carbon and instantly know what its formal charge should be. Now let's look at this with oxygen. Most of the time, we're going to see oxygen with 4 bonding electrons and 2 lone pairs. Have a formal charge of 0. So that's like oxygen that we've seen in all of our examples so far, where it will have maybe 2 single bonds around it and 2 lone pairs. Or maybe it will have a double bond to it and 2 lone pairs. So regardless, if it's got 4 bonding electrons, 2 lone pairs, its formal charge is always 0. If it's got 6 bonding electrons and 1 lone pair, trying to think about that for a little bit. If it's only got 1 lone pair around it, it's giving extra electrons to do something else. Its formal charge will be +1. And you saw this in general chemistry, for example, hydronium. H3O plus, where that oxygen has 1 lone pair, has a formal charge of +1. Now, as a side note, I like to put circles around my charges. That's not a convention. That's not something you have to do. I like to put circles around it so that it like delineates it from the rest of the structure, but that's not something you have to do. But again, anytime you see oxygen, a common way you'll see oxygen like that in OChem is you'll see it with an extra, like with like something like this. Again, 6 bonding electrons around it and 1 lone pair. Now, if you see oxygen with 2 bonding electrons and 3 lone pairs, it will have a -1 charge. And again, going back to GChem, that's something like hydroxide. So it's got a single bond to hydrogen and 3 lone pairs. So anytime you see that, where oxygen has 1 bond, 1 single bond, and 3 lone pairs, it's going to have a -1 charge. And then one thing I want to highlight, kind of notice the trend here, is that you generally will not see charges higher than 1. Okay. Carbon with a +2 charge doesn't exist. Carbon with a -2 charge doesn't exist. Okay. So your charges max out at 1, whether it's -1, +1, and then most commonly 0. And then let's do this with nitrogen. So when nitrogen has 6 bonding electrons and 1 lone pair, its formal charge will be 0. Most commonly, those 6 electrons will be like single bonds, and then it will have a lone pair. There are some other ones we'll get to there where you'll have a double bond to nitrogen or even a triple bond, but it's kind of like more of an exception than a rule. If nitrogen has 8 bonding electrons around it and no lone pairs, it will have a plus charge, +1 charge. Remember the ammonium ion from general chemistry? Hopefully I'm not traumatizing you with all the polyatomic ions you had to memorize. Ammonium is NH4 +1. The nitrogen has a formal charge of plus. So in general, when you see this template where it's got 4 single bonds around it, that nitrogen will always have a plus charge. And then on the other side of that, if there are only 4 bonding electrons around nitrogen and 2 lone pairs, then it will have a -1 charge. So that's something like this, where nitrogen has 2 lone pairs, 2 single bonds around it, or total, I should say, 4 bonding electrons, and it'll have a -1 formal charge. So that will kind of do it for this lecture. When we come back, and I highly recommend, you read ahead, we're going to talk about bonding in organic chemistry. So we're getting into things like valence bond theory and molecular orbital theory. Both concepts were covered in general chemistry, but we're really going to highlight them here in organic chemistry. So I will see you back then.